Welcome everybody to the afternoon session. I'm Ali Fatemi. I am at the Kennedy Krieger Institute and the board member at ALD Connect. We're going to get started the afternoon session essentially now with the speaker and then industry panel, and then we have.
All right. Thank you very much. I'm very excited to talk about some of our machine learning work. Jumping straight into it, I'm going to show some of the results and the methods, specifically the challenges and what's possible with these wonderful machine learning and deep learning methods. So for the first data set in our larger project, primarily we're using sensory motor data, clinical data, and our goal with these longitudinal data is to understand, label, and then predict disease progression over time. So there's a pipeline that we've generated, and this has 4 distinct parts. So the real challenge with longitudinal data is transforming that data firstly into numbers that one can crunch. You know, these are very large data sets with lots of variables. Secondly, because of the large amount of variables for sensory motor data, for metabolomics, reducing them to an optimal size so that, you know, if we think about what is our end goal, is I like to think about it as what if we had an app, right? Where you put in your variables and it can tell you you have this and this percentage chance of being a progressor or progressing over the next few years. So the goal is to develop this kind of app that can help clinical trials find optimal patients, and then eventually, once there is, you know, therapeutic data out there, to model and predict response to therapy. So after we do the variable selection, then we look at clustering. Now, clustering here is of vital importance because unlike other machine learning, deep learning projects, it's very hard to nail down, especially in this time frame, what is progression? Cross-sectionally, there are great variables that we know and use clinically, EDSS, global scores, severity, these kinds of things. And they're great, but these are ordinal scales that are meant to encompass the entire lifetime. And also, you know, filtering out noise, those kinds of things. You know, is it really meaningful that the EDSS changes by 1 over 1 or 2 years? And so we use the clustering to generate these labels, progressor, non-progressor, and then varying subclusters or degrees of that. And finally, after generating these labels, we want to be able to pour in data and then pull out, you know, a classification or a prediction. So just to briefly go through in 2 points, how do we transform these data? So on the left side, we see, these are for one data set. Each of the blue points would be one patient's, maybe 100 variables that they have. And so we take these, and one of the first steps we do in order to reduce noise, take care of outliers, and we look at measures like heteroscedasticity, is we look at a delta over years and the mean delta. So we're looking at how will these patients change over the duration of 1 year? But then we use, 5 years of data to generate that 1 year, that 2 year, and that 3 year trajectory. So by this time, we've generated multiple, and we call them data sets. It's going to become a little bit more involved as we then look at each of the variables. Now, here I have to be very careful because there are 2 worlds of AI science and medical science. And the nomenclature feature is the nomenclature variable. So when we talk about feature selection, we're talking about variable selection. So in our second step, we want to reduce the number of variables. I'm just going to, from this point on, call them features. We want to reduce the number of features, but we want to do this optimally. And we want to use an unsupervised method. And the beauty about unsupervised machine learning is, in essence, you let the data speak for itself. You're asking the data, show me which, and show me mathematically, which of these features can best ... So I'm going to talk about the ... i.e. how do we optimize for these feature selection methods. So some of the methods we use are classical statistics, because there's a lot of black box about machine learning methods. You don't know why some things come out. So we go in lockstep, a kind of tandem where we look at classic understandable things like modality and centricity. At the same time, there are wonderful machine learning tools that will say, okay, give me the best mathematical method to select the features that are able to. And then what we want to do next is cluster them. So for each of the data sets, remember we have delta 1 year change, we have their 2-year trajectory, their 3-year trajectory. For each of them, we create a different feature set. For example, here we've created a feature set where we said, let's start with a max number of features and reduce it by 1 every time. So we create, in essence, at this stage, we've created 5,000 different data feature sets. So these are 5,000 variations of the longitudinal trajectory of AMN patients. Now we get to the clustering. So we've got these 5,000 data sets, and individually we look at the data set and we want to say, okay, how are they similar? So on the left, we have this, it's called a k-means clustering. And what it does in essence is it'll generate a cluster by saying which of the data points are closest to it. This representation, this is 2-dimensional space. You have an x-axis and a y-axis, but in reality, we're dealing with 100, maybe 1,000 variables. So we can't represent these hyperplanes, but in essence, we're doing the same thing. So over multiple dimensions, we're looking at which data points, i.e. which trajectories, are they getting better, are they getting worse, are similar. At this point in machine learning as well, the methods, the nitty-gritty every day of what we need to do is optimize hyperparameters. Hyperparameters are settings of the task that we give them. The big one here is how many clusters do we want? So if we say, and for starters, we want to start with 2 clusters just to be able to see, can we cluster them into one other? Also importantly, at this point, we don't know what those clusters mean. We have to then look at the data and say, okay, in what way are these clusters similar? Now we can help ourselves there because we know for every variable, at least for the clinical ones, that we can adjust them so that higher, for example, is worse and lower is better. And then finally, after we've done our clustering of our thousands of data sets, we need some sort of validity, because this is all spooky so far. This is black box. It's spitting out numbers. It's spitting out patients telling us these guys are progressors, these are not. How do we get any sense of, is this accurate? And the way to do that is to repeat same data set, different feature set clusterings, and see, do these same patients cluster in the same groups repeatedly? And we do. So that's the figure at the bottom right, where the blue repeatedly cluster as quote unquote worse as progressors. So we can, with some sense of confidence, label the groups then and say these are progressors and these guys are non-progressors or slow progressors. So here's the clustering results of our 2 years, our delta 2 and max. So we've used the max features just for the sake of showing the data. And we're looking at optics for feature selection and k-means clustering. Now, there are 2 interesting things that jump out here, and this is pervasive. We looked through hundreds of data feature set results that show that there is not a strong correlation between the 2-year mean change in EDSS and those measures that cluster strongly. And those measures that cluster strongly are worsening in the gait measures, velocity, stride length and cadence, hip strength, and spasticity from clinical testing. This is the ACWA scale. Again, this is the validity testing that we run on it. So again, all of this is unsupervised, which means that we have not told this data what is important and what is not important. We've let all of the unsupervised methods kind of like float to the surface and tell us which variables or which features are important for us. So we've clustered and we've used these clusters to generate our labels for our patients, progressor, non-progressor. And with that, then we can start on the big part, which is designing and training a deep neural network. So now there's a little bit of a difference between what we've done so far with this unsupervised machine learning and deep learning. So deep learning is this wonderful trained network where you pour in information, and by black box methods, black box in the sense that we cannot at a certain point go in and look at the data and say what happens to it exactly, but we can measure the outputs and we can train the outputs. And these are those networks which work with superhuman precision. 2018 Nature paper, dermatology, pictures trained with a network, something like 90% better accuracy than the board certified dermatologists, that kind of thing. Deep learning networks are ubiquitous nowadays. They're baked into so many things from, you open your email and automatically things like times and dates are highlighted, speech recognition, Siri. I mean, these are ubiquitously in use, and the use of these has exploded over the last probably 5 years. Training a deep learning network means that we have to take now our labeled data and we run it through, and each of these dots is called a node. And so basically what happens is you have a number, which is our trajectory or our delta for how a variable changes, how a feature changes, and apply maths. So the apply maths comes in two parts. One part is called the architecture of the networks. So each of these round circles is called a node, where data in, apply mathematical formula, and that formula is called a weight, which is a function. So you do a specific function, add to it, subtract, multiply, etc. And then there's an output, and that goes to the next node, and so on and so on. And the training involves you run the numbers through, and you start a completely randomized function, and you get an error. And then you take that error and you want to correct it slightly each time. And that's the training, that's the iterations of each time you run it back. You propagate it backwards through the network and say, okay, you have a picture of a dog and you're telling me it's a cat. That's wrong. It should be a dog. And so it slightly adjusts that number each time. And so that's the iterations. And eventually dog goes in and dog comes out. Now for us, we put in progressor in, and that progressor data is, a series of their trajectories or a series of their static data, and we want to classify their trajectories. So we know that it goes in as non-progressor and that becomes progressor. That's wrong, and so that's how we retrain these networks. For the architecture, the big challenge here in deep learning networks is that we want to be uncertain. We need a level of uncertainty about how likely is it that what you're telling me is true? And in the world of science, there's this wonderful Bayes theorem, which is, in a nutshell, the more data you get about something, the more you're able to change your opinion about it. And so your quote unquote opinion is a probability of it being true or not. And so the Bayesian neural network, which is a network architecture that has been in use for a couple of years now, for each output, and this is the really cool thing, for each output, it tells you there is a probability of, for example, this patient progressing. For example, patient comes in, we put the data into the network and it says 85, 90%, or 70% probability of progressing in these symptoms over the next few years. The function we use for the weights is called a ReLU function. It's very common, most commonly used, and we can train the architecture that we design here using it. So we had 5,000-ish data sets. Which one do we train? We train all of them. So that's the computational expense of this. That's what takes days and months to have this done. And when we have these results, we're asking questions about optimization. Specifically, we want to optimize which pre-processing, which number of years. We want to optimize our clustering. And then finally, after we do all of these tweaking, we need to still go back and look at the data because we're using stats hand in hand to ask, does this make sense clinically? So does the feature data set that we use, are these relevant parameters? Because so far we've used unsupervised learning. So this is our checkpoint where we do that. So looking at the results of this Bayesian neural network that we trained at the Moser Center, we have a 1-year prediction accuracy of 90.4%. So what this means is that when we pour in somebody's data, and this is using 34 features of clinical sensory motor data, we can, with a 90% accuracy, predict whether they will be a progressor or not in the next year, and a 71% accuracy to predict that over the next 2 years. Then I want to look at some of the data sets. So this is currently going into publication. We've just submitted this. These are cross-sectional blood plasma data from 14 AMN and 6 control. RNA-seq, we're looking at 2,500 microRNAs and 800 metabolites. So again, massive data set. One of the first things we did was classic biomarker discovery. You know, we regress against EDSS and global scores as cross-sectional data. This is wonderful. And our top hits by looking at those that have potential of being biomarkers are A on the right side at 7-alpha hydroxy 3-oxo 4-cholestinoate is 7-HOCA, a cholesterol derivative, DHEAS, hypoxanthine, and an miRNA 4325P. These have previously been identified as potential biomarkers for other diseases, and they have very interesting physiological tie-ins. But what I want to get to is using this data with machine learning tools, because when you use one biomarker, you know, one loses out on the collective information that is between all of the biomarkers. So we went really simple. Instead of a very complex deep learning network, we said, let's take the simplest classification tree, and we used a CART, a ordinal classification regression tree. And in essence, what this method is able to do is it creates a binary split, and it selects the variable that is best able to split into classifying a specific, and here we want to predict EDSS. So this method will say this variable can predict this EDSS, and so on, and so on, and so on, and then create a tree of them for each of the EDSSs that are present in the data set. So this is what we get. And I have to be very careful here in saying that these specific metabolites that are listed here are specific to this data set, in the sense that these are selected in relation to the other metabolites. So, you know, a very big grain of salt here. Using this to predict a patient's EDSS, so we pour these metabolites in, and these are what, 5, 1, 2, 3, as we're counting down the tree, 1, 2, 3, 4, 5, 6 metabolites, can predict with 83% accuracy using the CART tree, which is an algorithm to predict the EDSS. Now, again, validity observations, how do we know this is true? Well, in this case, we kept it simple so that we could go into each of the metabolites and say, does it make sense? For example, here, the validity observation, bottom left plot, is our top candidate, which tells us the method has selected this to be able to identify EDSS 0 or our controls, and we can see that's true. And then on the right side, this is the step where it can identify an EDSS of above 4. Yeah, so as a conclusion, I think these data, or these results demonstrate that using not just one biomarker to predict cross-sectional, but then looking at trajectories, using multiple biomarkers, the relationships between them has a lot of potential. If we can do this with such a small patient cohort, then I think there is great potential to use a lot of biomarkers.
Okay, so sorry it was a little disrupted at the end. There's a couple of questions. There is a question by Isaac saying, have your models surfaced unexpected contributing features? Thinking of SHAP analysis, not sure what that is.
There are very unexpected features that arise, but we try in the methods that we approach. So this is a great question. I love this because we had this exact discussion of when we do our unsupervised clustering, we can go at this in two ways. And the first way is the optimization way, where we can say we want to create the best data feature set that allows us to predict. And the other way is like the classic exploratory way that one does with RNA-seq nowadays. Yeah, and there are a couple. I mean, even these variables that floated to the surface, we had an idea from simple regressions or multiple regressions that these are powerful. But the fact that in repeated data feature sets that these don't correlate well with changes in EDSS over 1 and 2 years, I mean, I think that's an exciting or an interesting finding.
Okay, there's a second, I think, very good question by Dr. Eichler. Nice talk. Is this telling us that we should be designing trials in new ways? Any thoughts? Informing stratification or new combined outcome/biomarkers?
Yes, I think that's an excellent question. So I think there are two specific points here. Number one is it highlights the value of pilot biomarker data for trials. In doing so, even pilot data can be used to find aggregate, and not single aggregate biomarkers, but a series of biomarkers which individually may not well represent disease trajectory, but collectively could be used to. And the use of that, my second point is, in designing the trials, these things can be used not just for biomarker selection, but for patient selection as well. So one could theoretically model the expected trajectory of a patient with and without therapeutic intervention. With natural history.
Great.